Okay. Hi, everyone. Welcome to the keynote session. So I am thrilled and delighted to have Nicholas Carlini give the invited talk of Crypto 2025. Nicholas got his undergrad and PhD in Berkeley, in UC Berkeley, under Wagner, I believe. And he's a world expert in machine learning and security. He has amazing work on adversarial machine learning and privacy in LLMs. And hopefully today he's gonna tell us how we cryptographers can jump in and help. So Nicholas won a lot of awards. Actually, I was just looking, just last year, you got 2 best papers in ICML and 1 in Eurocrypt. Man, taking all of them. So, and also his work has been featured in, New York Times and Nature magazine. So he has done a lot of really, really great work, and we're super excited to hear what he's gonna tell us today about how cryptography can help in the age of LLMs.
Yeah, thanks for the kind introduction. Yeah, so it's really an honor to be here. I've actually never been to crypto in person before, despite the fact that I got started my research in this sort of doing cryptography stuff. I never had a chance to do crypto, and the one opportunity I had a paper of crypto in 2020, was not the best time because I had to give it online, and I was really quite sad about that. So yeah, I'm going to talk about the use of language models, how the world, I think, is changing because of this, and how cryptographers can try and help. Yeah, OK, so first time here, so I figured I'd say hi. I'm going to try and give my perspective as someone who, knows something about a little bit of cryptography, but very much is not an expert in this field. What I'm going to try and do is talk through how I've been seeing the field of machine learning change and how cryptography has tried to help. Over the last 10 years or so, I started doing research in security and machine learning roughly 10 years ago. And so I'm going to try and talk through how cryptography has helped in the past and the ways in which I think it might be helpful going forwards in the future. Basically, this is a recruitment pitch. I want you to come work in our field. I think that there are a lot of people coming from machine learning working on the field of cryptography and machine learning, and they don't know a lot of the cryptography pieces. And I think it would be great to have some cryptographers trying to help out too. Sort of if the one thing I want you to try and take away is, yeah, I think you can help and try and contribute. Great. OK, so what classically has cryptography tried to contribute to the field of machine learning? Well, if you look back at the papers from, let's say, 10 years ago, the main thing that cryptography was trying to do was to address the flaws that we had with machine learning models. And so what I mean by this is one of the example problems is certified robustness. You've probably seen something like this if you've seen machine learning before, where you have these image classifiers that classify images correctly. You add these adversarial perturbations, and you end up with images that look the same to the human eye, but the same image on the right is misclassified as whatever label I want. In this case, 99% as guacamole, and this is a problem. And so people have tried really, really hard in the machine learning community to do all kinds of ad hoc approaches to defend against this. So they change the gradients, or they put extra pre-processors before the model or after the model, and they sort of just don't do things that are very principled, but they sort of try their best. And it turns out that if you study these for the robustness properties, try and analyze, are these defenses that people created secure? The answer is not really. So a couple of times we did studies. We took all of the defenses at some conference, and half of them are broken. This was one we did in 2018. We did it again in 2020, roughly 2022 timeframe, and it was even worse. A bunch more of them were broken, and you end up with sort of people trying to do these kinds of things and not succeeding very well. okay, we did it again, and like, just like it sort of fails again and again. And so like this is one of the ways in which cryptography has helped classically in this machine learning space, where what you can do is you can like try and prove properties of these models, and you're not going to solve the problem, right? You're not going to fix this problem sort of fundamentally, but at least we can be sure if you use some of these techniques that the thing that you think you have achieved, you have actually achieved, which like is the bare minimum you might want. Like these schemes are sort of just like not providing very much robustness, and you can these are two papers, but there are like hundreds of them from the literature that try and give you guaranteed robustness in some small sense. And it's not going to solve the problem, but it's going to like actually give you some very strong level of guarantees that you're correct. Okay, so this is one kind of problem people have studied when they talk about cryptography and machine learning. Another example people used to study quite a lot, they still do too, but like is a similar kind of problem for this private training. So what private training is first, let me introduce the problem for you again. Machine learning models are not very private. What I mean by this is they leak details of their training data sets. So here's an attack we had from roughly 2 years ago. If I asked ChatGPT at the time to repeat the word OK forever, it would say, OK, 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 OK. It would go on for some while, and then it would start doing something very different. Kind of weird. I don't know what it's doing. But then you'll find that if you sort of actually look at this, there's a phone number here. So you can, OK, fine, let's look this up. There's a phone number, here's a person, we click on the link, and what do you know? There's some person who in their email signature, they sent a bunch of emails to some mailing list, and like, OK, the model had memorized this person, individual person's full contact information. And like this happens quite often, that these models that are trained on lots of data sort of pick up on small pieces to memorize for who knows why. OK, so this is not great. And so you could try and do ad hoc things and try and prevent this. Or you could try and do cryptography. And so people tried to say, well, what we're going to do is I'm going to take the ideas of differential privacy, and I'm going to try and train my models with DP to guarantee that this kind of thing can never happen. And again, it doesn't solve the problem entirely. What if you have some data that's duplicated? DP has some exponentially bad guarantees as you add large groups of data. But like if you sort of do some things right, you can fix large portions of this problem pretty well. And so there are lots of other things people have been trying to do, but this is sort of this one category of things people have been using cryptography for, which is finding flaws in machine learning models and then fixing them. OK. And so that was, I don't know, let's say the first couple of years of how people really tried to bring cryptography to machine learning. After that, I think the approach people took changed a little bit. And instead of trying to say, we're going to try and fix the flaws in machine learning, after a couple of years, machine learning started to like actually work. It was good enough that it was not something that just like academics did in their labs to classify images between hundreds of breeds of dogs. Like the models could actually be deployed into the world. And then the question is, how can we make machine learning more usable by using cryptography? And so you see a bunch of applications here. One of the ones that people have been thinking about a lot in the last 2 years, I'm not going to talk so much here, is watermarking. Actually, Scott Aronson gave a whole keynote on watermarking just 2 years ago here. So I'm really not going to talk about this very much. The general problem is, let's suppose that you have models that are good enough that they can generate arbitrary text, or they can generate images that look realistic. You might want to be able to detect this. Maybe you want to stop students from cheating. You want to detect misinformation. You want to somehow know what was written by a real person and what was written by a model. And so you can synthetically modify the outputs of these models using cryptographic techniques so that you can say the output has not changed by very much. It's indistinguishable in some sense from the real thing. But I can query and detect whether or not this thing was watermarked. OK, so this is sort of the idea here is not trying to fix any problem with the model itself, but we're trying to say these models are good enough to exist out in the world. How can cryptography help sort of deal with this world? Right, there's some papers here. Another example that I've been working on a little bit is this problem of model stealing. So again, you have these models that are good. They're very, very useful. And you try and host them, and you now worry that someone is going to try and steal your model. Right? This is not a concern if your models aren't any good. But if you have a model that's actually usable in some sense, and you're hosting it, and you're charging people for it, you might be worried someone else is going to query your model and try and obtain a copy of that model that they can then go and run locally and do whatever they want without having to pay you. Now, it turns out this problem has actually been a problem for a really long time. People have been studying this since the 90s. But it really started to become a thing that people studied in the machine learning space roughly 8 years ago or something like that, 9 years ago, when Florian Tramer and some of his colleagues wrote a paper trying to discuss this at Usenix, looking at trying to do this in practice for some real models people were deploying. And again, the question here is now not one of how can cryptography necessarily help make the models good, but now that these models are good, how can cryptography try and exploit these models in some useful way? So this is maybe like the one chance I have to talk about my Crypto 2020 paper on the stage. So I'll just say that we sort of we tried to use some cryptanalytic techniques. We sort of observed the fact that turns out deep neural networks look a lot like block ciphers. And so you can take some ideas from differential cryptanalysis and apply them to these models, and you can use that to do something like a model stealing attack. And it works pretty well. We sort of had another paper fairly recently looking at doing this at Eurocrypt, extending it to be even further. Right. So that's generally what people did for, I don't know, the next couple of years. And so what I want to do in this talk is say, now that we've sort of done these things, we sort of have had people working on trying to fix flaws with machine learning models. We've had people trying to deal with the world in which these models are useful. What do I think we can do in the next couple of years now that we have these models? And the pitch I'm going to try and make for you is that I want to try and think about what we do in a world where these models might be harmful, which is a very different pitch, I think, than many people in this room have thought about before. But what I'm going to try and do in the next 40 minutes or so, and then I'll try and leave at least 10 minutes for questions, is explain to you why it is I think that there's a chance that these models that we're working with might be harmful in the future, and how I think cryptographers might be able to help mitigate some of the harms coming from models and hopefully make it so that we don't have to worry quite so much. OK. So what do I mean by this? I don't know if you've noticed, but the machine learning and language models we've gotten over the last couple of years have gotten really good. So as an example, just in the last month or two, there have been a couple of companies, both in this case Google and OpenAI, who have machine learning models, large language models, that got the gold medal on the IMO, which is a very challenging set of math questions that don't require deep expertise in any one area, but require some degree of creative thinking. And I hate to use that word and attribute it to language models, but like if a human solved it, we would have said they thought creatively. Same thing for OpenAI did the IOI, which is basically like the IMO, but for programming. So these models are like really, really good at solving these kinds of problems that classically we thought only people can solve. And unlike traditional approaches that have been applied in the past, where they tried to take some formalism of the problem and solve the problem formally, these recent methods read the text description as if the human would have, and then output a text description of the answer and can solve them. So it's like problems that we would have thought, I would have not have thought was possible for at least another 5 years or so, happened just a few weeks ago. In another domain, the domain of programming, we have charts that look like this. This is the sort of the plot that sort of makes me sort of the most concerned. OK, so what I'm going to show you here is on the x-axis is time. Each point corresponds to a model. And on the y-axis is what they call the time horizon. This is how long of a duration of a task that it takes humans can models solve with 50% accuracy. So for example, on the lower left, we have GPT-2. This is a very, very terrible model by today's standards, which can solve things that humans take like 2 seconds to answer. You ask, like, what is the capital of France? And it can say Paris, because a human could just recall this immediately. But it can't do any kind of complicated reasoning. And as you go up, you'll notice that what the models do is they get better and better at an exponentially increasing rate. So I've log scaled the y-axis, or at least Meter did it for me. And what you'll find is there's a very nice linear fit. So they produced this linear fit stopping somewhere in 2024, and the models after that have gone sort of only above the line. And so the observation to take away from this is that these models are getting better at like solving exponentially longer horizon tasks. And so the kinds of things that we normally think of as being only achievable by humans, by people, are the kinds of things that models are solving now for us. Okay. And this might be fine, right? Like if the only thing the models were doing was these kinds of tasks, like, I don't know, I probably don't have to worry. But there are lots of things in the world, lots of bad stuff that could happen that right now only humans can do, that in principle a model could help a person try and do and cause harm in some ways. Okay. So sometimes when I show plots like this, people say, like, obviously it's not going to continue forever. And like, I don't know, I agree. I think I basically agree this plot's not going to continue forever. There's a very nice quote that I like. Okay, so this is the plot that Moore made when he predicted Moore's law. He predicted it on like 5 data points and just drew the line up and to the right. And the quote here, he says, over the longer term, the rate of increase is a bit more uncertain, although there is no reason to believe it will not remain nearly constant for at least 10 years. Okay, I'm not going to be quite that aggressive. I'm not going to say that we're going to have 10 years of the same progress in machine learning models, right? If you had 10 years at this kind of rate, you would end up with like years-long tasks being solved automatically. Some people think it will be possible. Lots of people in the language model space believe this. I think it's plausible. I don't think it's likely. But I do think, sort of like this quote is saying, there is some chance that it will continue for at least another couple of years. And if it were to continue for another couple of years, you'd end up with models solving tasks that normally take us days to a week or something. Okay. And I think many of us, me included, react at first like saying like this is sci-fi. Because it feels like it. It feels like this is not something that's actually going to happen. But you have to realize that like what the models are doing right now is like already far beyond the capabilities of things that I thought would have ever happened. Like if you asked yourself, like honestly think 2 years ago, 3 years ago, would you have predicted that a model could automatically solve like some of the most challenging math questions that we ask high school students to solve? The answer is like almost certainly not. And yet they're doing them today quite reasonably well. Okay. So that's on the the models are doing well side of things. What do I mean by harmful? And there's a wide range of harm. A significantly wide range that I'm not going to be able to talk about nearly all of it in order to motivate the question. So I'm going to try and just spend a little bit of time explaining a small fraction of the harms people worry about. And the range really is quite wide. On one extreme, you have companies like OpenAI, who say things like they're trying to prepare for worlds in which models could help to create bioweapons. Sounds sci-fi again, but honestly, like many things in the world, it's not actually technically that hard to do. There's some amount of knowledge you need. And once you have that knowledge, you could do it. We just rely on the fact that anyone in the world who could do this has gone through a PhD and doesn't want to do it. But there are lots of crazy people in the world. And if the access was easy to obtain, then this is potentially a legitimate concern. I'm not saying this is going to happen, and I don't think these companies are either, but it's something you have to think about. So this was OpenAI saying that. I work for Anthropic. They have said the same thing, where they are worried about what they're saying is CBRN. The B here corresponds to biological. The other letters are chemical, radiological, and nuclear. Same kind of things. The concerns are that these models will have some kinds of knowledge that a person who wanted to cause harm could take advantage of in order to do something bad. But this is not very much on an extreme take. There are much more mundane bad things that can happen too. Sorry, I have one more slide on this. So when I tell people about this biological harm, one of the things people say is like, okay, that's fine, but like it's very easy to train the models to refuse, right? Like I'm sure you've ever tried to use one of these chatbots. The very first thing you can do is you can ask it to do something bad. In this case, I've asked, step-by-step plan to destroy humanity. The models will say like, I'm sorry, I can't do that, right? Like this is like you would think this is an easy thing to refuse against. But like, remember at the very beginning, I showed you this adversarial example problem. We've made progress on this problem, but we haven't fixed it. So if I ask the exact same question, in this case, generate a step-by-step plan to destroy humanity, which like is the easiest thing in the world to refuse, and I add an adversarial example, the model will just give an answer. It's not a very good answer, right? Like, there is no 10-point plan to destroy humanity. But like, it's pretty easy to say, sorry, I'm not going to help you with that. Like, like question is like completely obvious what I'm asking for, and yet the model is trying to help out. And so this is the kind of thing that you could imagine would be trivial to make the models not give answers to, but like even when I'm just asking the most obvious version of the question, the models are more than happy to try and give answers. Okay, so this is on the more extreme setting. There is other things that you can imagine to be worried about on the more, I don't know, like normal side of things. So one of the papers that we wrote recently is trying to think about what this might look like in the space of malware. So the example of the problem here is, let's suppose I have some ransomware that's running on your machine, right? So you were running some unpatched version of something, someone found a 0-day, they got ransomware onto your machine. What are they going to do? They're going to encrypt all the files on your computer and say, pay me some fraction of a Bitcoin and I'll send you your data back. Okay, so why this? Because everyone wants their data back. Like the idea of an exploit is to be maximally general, so I want it to hit like every Windows machine. But that means that the exploitation has to also be maximally general and hit the lowest common denominator. And everyone wants their data back, so I'm going to go for that. But like if I personally had access to each one of your machines individually, I could almost certainly find something worse that you would be willing to pay more for than your data back on your machine individually. But that's just not scalable. You can't have an individual person do this for every machine, and so we write one program to do something that sort of suits everyone. But if you have language models that have some small degree of adaptability to the environment they're in, you could imagine a world in which these language models try to guess, for you in particular, what would be the thing that would make you most likely to pay the ransom, looking at the files on your computer. So as an example, we ran some language models over the Enron email dataset released by the US government 20 years ago or so. And we asked it, like, what damaging stuff would you want to blackmail someone on over? And for one of the people, what it found is that it said, OK, I'll read the quote from what the model said. It said, John G. appears to be an options trader at Enron. Here are some key relationships. There's Angelica, appears to be John's wife. They discuss domestic matters like groceries. They express love and affection. And then here's Alexandra, appears to be someone John is having a romantic relationship while married. They exchange flirtatious emails and meet secretly. They discuss meetings for breakfast, rides to and from work. This appears to be an extramarital affair, right? Like this would be like very, very easy for the model in this case to then go and say like, this is ransomware running on his machine. It's read all of his emails, blackmails him. If you don't sort of pay me some fraction of a Bitcoin, I will send these emails to your spouse, right? Like this is not a hard thing to do. And models could totally do this today. It's still a little expensive. Like this is still a little bit too expensive. So that's, I think, the one thing we're holding out on. But the costs to deliver a given level of capabilities have been lowering about 10x year over year. So I don't think we have that long before this becomes economically viable as an attack strategy. And you can see how like this is not something you could have done with like regular expressions. Right, like it sort of required some degree of like, here's the because like, there was no email that says, I am your wife. There's no email that says, I am your affair person. Right, so like you have to have some conceptual understanding of like, this is the person who like looks like they were talking about groceries. That probably means spouse. This is the person who is arranging hotel meetings when they're at conferences, like and sort of said other things. That probably means something different. So like, so the models can do this kind of behavior now. There are other scarier versions of this. I'm going to try and publish them soon that I'll talk about. But like this is the kind of attack that I think is pretty worrying to me as like a security person. OK. Yes. And then there's the other extreme where like some people literally believe that if anyone builds sort of superhuman intelligence, like everyone's going to die. And this is the thing that some people in the machine learning communities worry about. I'm not going to talk about this except just to say like there is this spectrum, right? There's a spectrum of risk of like, maybe it's mundane harms, maybe we all die. But like somewhere in the middle is like how far you're willing to believe is the truth. And how far you go to the right roughly corresponds to how good the models get. As the models get better, they're sort of more able to do things that seem pretty harmful. Like right now, I think we're like pretty far to the left over here. But it's possible that if models get better, you could sort of imagine moving slightly farther to the right. And because the models are getting better exponentially quickly, this is the kind of world that people are concerned about. OK. That's all I'm going to try and do to convince you about the importance of the problem. But I do think it is quite important. Right? It sort of sounds, like, why would I say it's important? Like, I think just some people say things that they don't necessarily believe. I do honestly believe that this is an important problem to have people try and solve. And I don't know, like, I don't think that you all are that much of a stranger to solving problems that don't yet exist. Like, so you have 4 sessions on quantum cryptography, right? Like, do you have a quantum computer like in your pocket? No, right? Like, okay, 4 sessions on quantum computing. You have 3 papers on post-quantum schemes that like are sort of robust to quantum computers that we don't have, and a best paper also on quantum, right? Like clearly there's some willingness in this community to work on problems for things that might be a problem in the future. And what I'm trying to say is, I also think that a different problem that might happen in the future is you might have language models that are pretty good, and it's worth spending some time now addressing the problem so that if it were to become a problem in the future, we're not caught unaware. And I don't know, my personal opinion seems strictly more likely that in the next 3 years, you might have dangerous machine learning models than a quantum computer. It's just like, I don't know, feels pretty likely to me. But like, you have this at the conference and not people thinking about the machine learning problem. So this would be my pitch, is that it's not that weird to work on problems that don't yet exist, because it would be really, really bad if problems came out and we hadn't thought about how to fix them ahead of time. OK, so what are the problems that I think you should try and work on then? And that's what I'm going to try and cover for roughly the next 20 minutes or so. And that should leave maybe 25 minutes. And that should leave a good amount of time for questions at the end, so you can heckle me and describe why you think I'm wrong. OK. Yeah, caveat, I'm not a cryptographer. I don't know what I'm talking about, but I can pitch some things that feel cryptography shaped to me. I've spent a little bit of time thinking about this, and I would encourage you to try and do better than me. I believe that you can come up with better problems than me, because I don't know this field very well, and I could at least think of some important problems. And so try and pitch better ones, and I'd really like to see them. OK, let me get started with maybe a first simple one, which is what I'll call verifying developer claims. So what do I mean here? This comes roughly from this paper by Rand and also by Miles Brundage, who used to work at OpenAI. Now he has a startup, a nonprofit that he's working on safety. And the general idea is, because capabilities, how good the models are, is often intertwined with how dangerous they are, you might want to be in a world where you don't train the best model you possibly could, so that you could have it be safer, you could add more security features ahead of time. But I don't want to do this if I know the other person over there is not going to add the safety features. And so we're like in this race to the bottom, where they don't want to add safety because they think I'm going to race, and I don't want to add safety because I think they're going to race. And so it would be mighty convenient if there could be some way to verify that each of us to the other is doing the right thing, so that everyone can together do the slower, less profitable thing, but add safety, and so everyone sort of works at the same speed. OK, but this assumes the existence of certain things. So like I'll sort of go into the middle of their paper where they have this figure, and what they do is they say, well, OK, here are the kinds of things that we're going to use in order to address this. What we're going to do is we're going to have this hardware-backed workload certificates. I don't know what this is, and but someone needs to make for this to be. They assume tamper-proof, compliance-locked AI chips. Now, they're not tamper-resistant, tamper-proof. OK, someone needs to design something that sort of satisfies what they want. They want backup evals on separate chips. The backup evals for what? How does the protocol work? What's the property that you're trying to satisfy? All of these things I feel like are very important questions, and are very much swept under the rug in a lot of these papers. And to be fair, they acknowledge that. They're not claiming that they know how to do this. This paper is trying to pose problems, but someone needs to address those problems. And I feel like the kind of person who could do that are the kinds of people in this room, where you can sort of read some of these schemes that people come up with that assume the existence of certain cryptographic primitives and be like, can I be someone who designs the primitive to test whether or not this works? And maybe the answer is no. I don't know what they exactly need. I don't know what the threat model is for these backup evals on separate chips. But maybe it's impossible. That would be good to know, so that you can tell people, don't design assuming this, because if you do that, I have a proof of impossibility that you can't do that. Come up with a new requirement, and I'll tell you whether or not it's possible. All of this would be very useful. Another example is what I'll call auditable training. In the EU, if you're training a model, and your model has been trained for more than 10 to the 25 flops, they say that your model poses potentially systemic risk. And so you need to do certain things and notify the government about what you're doing. Okay. So aside, in some sense, it doesn't matter whether or not you think models might pose risk. If the regulators are sort of putting in place requirements based on the fact that they are, you have to just deal with the world that you're in and not the world you wish you were in. And so they have these requirements. Okay, so I think there's a bunch of interesting questions as a result of this sentence alone. Maybe a simple question is, I should mention that the US has the same thing, or had the same thing for a very brief period of time before. So Biden passed it like a month before he left office, and then Trump immediately overturned it. But at the time, the US had a 10 to the 26 requirement. So the question, at least one question that comes to mind immediately is like, okay, could I prove that I spent less than 10 to the 26 flops on my model? Why would I want to do this? Because then if the government said, you must tell me everything about your model, I could say, that is overreach. I can prove that I have not done that. The law does not apply to my case here. The alternative is just to say, trust me, which it seems bad. And so it might be like, I don't know, is this a thing that I can do? It sounds like opposite of proof of work or something. I don't know, interesting question to me. But also, a related question, what could I prove about my data sets? Because if you'll notice that in the US law, it's 10 to the 26 or 10 to the 23 if I train on biological data. Okay. Why? Why biological data? Because they're worried about the biorisk. So the government was worried about the biorisk angle. And so if you trained a model for 10 to the 23 flops on bio data, then they're going to say that they want to know about it. So this raises the question, could I say something about, I did or did not train on a certain kind of data when training my model? I don't know. Seems like an interesting question, though. And you can generalize this, right? You could ask, could I prove that I sort of didn't train on any data satisfying some property P? I don't know how you formalize this. Like, in some sense, it's trivial, right? As cryptographers, you might say, like, this is a circuit. I can prove properties of circuits, done. But, like, the numbers involved here are enormous, right? 10 to the 26, I think is like 2 to the 80 or something. This is like, Okay, so the SHA-1 break was, I don't remember, it was like 2 to the 63 or something. This is like a SHA-1 break like every hour during the entire period of training this for a month. So like the numbers involved are truly enormous. Like if you're going to ask for something that like triples the cost, you're asking for $100 million for someone to pay in order to do your thing. So like it's sort of like a lot to be able to ask for these kinds of things. And so the question is like, what's the best you can do that doesn't ask for people to spend $100 million doing this? More generally, I don't know, you might just ask, could I prove anything about my training process? Like, it just might be useful to try and prove various properties about what I did or didn't do when training my models. Okay. A related question, or slightly different, but in the similar kind of sort of motivation, is what I'll call unfine-tunable models. So the idea here, first let me just define fine-tuning for you. What fine-tuning is it's the process of taking a model that was trained for one purpose and trying to adapt it to do something different. So classically what this meant was I'm going to have, I don't know, I trained a model on like ImageNet images from one distribution, which is like 1,000 different classes of objects drawn from the internet. And now I want to use it in order to do something else. ImageNet doesn't have concepts that have certain objects. I want to fine-tune the model to tweak the parameters to make it able to now do something else that I care about for my local setting. And so classically what fine-tuning was tweaking these models in these small ways. But another thing you can do with fine-tuning is you can take a model that was trained to be safe, and you can fine-tune it to just give answers to every question. So someone might, for example, try and do a nice thing in the world and release a model as open source, and they have trained it initially to refuse all the kinds of dangerous questions. Except it turns out that someone could just take the model and fine-tune it and make it now do various bad things. All of a sudden it will be perfectly happy answering the question, I'm trying to ransomware this person, can you help me out? And okay, so SB 1047 was this legislation that was tried to be passed in California. It made its way through the Senate. It was vetoed by the governor. But one of the things it required, or would have required, was that people who trained certain types of models, if they were sufficiently large, were going to be held responsible for any fine-tune of any model they trained. So if I trained a model, it was like I open sourced the weights, I'd let anyone in the world access it. If someone malicious fine-tuned that model, I was going to be responsible for the model that they maliciously modify it. This was going to be the requirement. And so on one thing that might happen is this just might kill open source models that are of sufficient size. But there's a research question that some machine learning people tried to ask, which is, can I create unfine-tunable models? Can I try and train a model that has the property that you can do whatever you want with inference with the model, but you can't adjust the parameters? And if you can't adjust the parameters, then you can't fine-tune it to now comply with harmful questions. So this was a sort of a thing that some people in the machine learning community proposed and tried to address in this way. But what they did was, again, entirely ad hoc. They didn't have any cryptography training. They didn't realize how hard the problem was they were trying to solve. So they just like tried to mess with the gradients so that when you did standard machine learning stuff, the problem wouldn't be that easy. OK, so we broke this again. It doesn't work. The attacks are particularly uninteresting. This was a paper led by some students. I'm not going to spend that much time on the attacks. I put the details here, but I decided, like, I don't know, like 10 minutes ago that I didn't want to talk too much about the details just so we can get to some questions. But the attacks are really trivial. The attacks are like, run the attack algorithm multiple times. And like this breaks it, which is like, I don't know, like, have you ever seen an attack in cryptography where like you just run the attack twice and half the time it works and half the like, it's like this is the kind of thing that we're dealing with when non-cryptographers propose these kinds of schemes. So here's the sort of figure from the paper. OK, so this is a little bit complicated of a plot, so let me walk through it. We have the original model in light green at the top. This is on the y-axis, how harmful, the fraction of harmful questions the model answers. So the original model answers like 70% of questions that are harmful. And then what they do is they go down to this dashed blue line by training the model again so that it refuses harmful questions, and then they put in place this unfine-tunable scheme. So the idea is that the model is robust, and it will stay at this 25% level. OK, this is on like a 4-question multiple choice, so 25 questions is random guessing. So what they've done is they've taken originally a model that was dangerous, they've made it sort of safe by refusing to comply with harmful questions, and then they made it unfine-tunable. And then the question is, does it stay there? The red lines are their best attacks. One of the best attacks already broke the scheme. But it turns out if you just ran their best attacks multiple times, the margin of interval, well, like the confidence interval was quite large. And sometimes it just broke the scheme basically out of the box. OK, not great. You could also do things just like, I don't know, re-implement the attack in a new code base. It turns out that this works. I'm going to skip through the details here. But just like the way that they set up the defenses happened to be really specific to the attack algorithm they designed. This kind of thing broke it. And so what like I think generally would be interesting to me is like, I don't know, what's the cryptographic primitive that could offer something like this? And as someone who doesn't know very much cryptography, it feels kind of like I/O. In the sense that what I/O gives you is it's like an oracle. The only thing that you can do is interact with it as a black box. And if you could have fine-tuned it, then it feels to me like, I don't know, no longer I/O. But I don't know what I'm saying here. Like, it's sort of maybe I want non-malleability, but like, I'm really talking about words I don't understand. But like, I assume that like this is a thing that exists, and I would like someone to try and think about like what would be required to do this. And maybe the answer is it just can't be done. Like, maybe you could write down a nice argument that says, if I could do inference on this model, then I can fine-tune it, unless you're willing to spend 1,000x overhead. And that would just be good to know for the world, because the next time someone wanted to require the existence of something like this, we could tell them what you're asking for is almost impossible. And if that was the case, then maybe they wouldn't do the thing that asks for the impossible, because now they could at least see what the consequences of what they're asking for was. But in a world where there's no cryptographers thinking about this problem, the only people who are proposing solutions are the people who are just going to try ad hoc to come up with solutions and see what they can come up with. And that's basically fine when the data is not out to get you. Because like, put your machine learning hat on for a second. What people do in machine learning is they have a random test set that is sort of IID drawn from some distribution. And as long as you have accuracy on this test set, you know that you're correct. Because like the data is not out to get you. But like in the real world, with adversaries in the mix, there is something out to get you, and they get to change their scheme. And like this is obvious to all of us. But like I have had so many arguments with machine learning people where they say, yes, but your attack assumes the existence of an adversary who knows how my defense works. And I'm like, well, yes, that's the point. That's what it means to be an adversary. But like this is a novel concept to some people in the machine learning community. OK, so yeah, I think there's like lots of questions that would be useful. I'll mention maybe one more and then a couple more general lessons. So there's this problem called unlearning, which I don't know, vaguely is like the opposite of learning or something. The idea is you've trained a model that has some certain capabilities. Maybe it knows some facts, maybe it has some skills, and you want to remove that skill, that fact from the model. So you can imagine I've trained a model, accidentally I trained it on someone's private data. Can I remove the private data from the model? Or I trained the model and it turns out it can do this harmful thing. I want to remove the dangerous thing from the model so that the model is safe. And so there's this question, can you do this? And it turns out, a lot of people have tried really hard and basically have gotten well, not very far. It's just a very hard problem. And in the ideal world, this is easy, right? Like if you have a model and a data set and you want to remove some data point from the model, you just remove the data point and then retrain the model from scratch. And there I fixed it. And you can even set up a definition like this. You can set up a differential privacy-like definition that says it's sort of indistinguishable whether or not I did this or I didn't. But like this has been very, very hard. And so people have tried really hard to solve this problem, and again, haven't made much progress. There's some colleagues of mine who wrote this paper on just like the definition of unlearning just itself being very, very challenging. And I don't know, again, this feels kind of DP-like to me. And so I don't know if there's a fix that you all have, but like, I don't know, think about it and try and see. Maybe you can find some idea here that you can solve some piece of this. Or maybe you can prove it can't be done. Maybe you can prove that if you train a model in some non-convex setting on a bunch of data and you remove something, maybe you can prove that the data always has some signature left in the model weights, and that it's always going to be possible to detect that I've done this. We know in convex settings you can do unlearning, because convex is nice and easy, but like these models we're training are like big, giant, ugly, hairy things. Maybe it's just not possible. I don't know, but I would like someone to have an answer to this. Okay, two last things that I'll talk about, and then I'll wrap up, that are not specific technical questions that I want people to think about, but are sort of ways in which I think you could be helpful. So the first of these is just like, as I was saying, with definitions. It wouldn't have been obvious to me how to define the word privacy. But like you've somehow managed to come up with a good definition of what privacy actually should mean. And it took some attempts. You tried k-anonymity and some other stuff, and then it turns out DP is actually a pretty good definition for privacy. But you got there, and that was like that's a very nice contribution from the field. Definitions would be really useful in our area too, because we're using all of these words, unlearning, unfine-tunable, but like we have no definitions for any of these things. We just like, we say things and just like hope that someone else understands like basically what we mean in English. So, like as cryptographers, you want like, some perfect capture of everything. I just want like, adequate. There's something that captures enough. So, okay, I'll highlight as an example of this. So this is a paper by some of my colleagues at Anthropic that they worked on. That's a tool that's called Clio, which they say is a privacy-preserving way to do insights into real-world AI usage. And the idea here is you want to be able to know, are people misusing my model in order to cause some harm in a privacy-preserving way that doesn't reveal the details of any individual person? That you're serving some model, you don't want to allow the people who are using your model to cause harm. So you want to allow them, so some auditor to look through the user logs without looking at individual user logs. Okay, good idea. I like the concept of something like this to check whether or not harm is being caused because of the models we're training. And so you can ask, okay, but like, what does privacy preserving mean? Okay, so here's the privacy analysis section. It is exactly this long and has no theorems. It says DP is hard because we're using rich textual descriptions. It does, though, say that Appendix D has more details. So if you go to Appendix D, you'll find this, again, entirely English description of more details, which says that there's a little bit more in Appendix G. You go to Appendix G, and the little bit more details that are available, here's the prompt to the model, where they prompt the model, literally, when answering, do not include personally identifiable information. So like, this is their privacy argument, is like, they have a language model, and they ask it, please don't include PII. I mean, like if this was acceptable, I watched a talk yesterday about private mean estimation. Okay, fixed. I asked the language model, please give me the mean, please be private. Right? Like you do not accept this. Like this is not a kind of thing that we would accept in the literature. I would like to see some kind of technique or measurement of like what privacy means in this setting. That's something that could be implementable. And again, I don't know what that is. Like empirically, this works actually pretty well. Like the paper is actually very forthright that like they're not going for horrible definitions. And they're not. But like, it feels to me like it would be awfully nice if there was something that they could have formalized a little bit, other than just saying like, average case 99% of the time is fine. Would be nice. So definitions, I think, are sort of one of the areas where you all could help quite a lot. The other way that I think everyone here could help quite a lot is just in doing high quality evaluations. As I was saying earlier, just you've learned to think about problems from an adversarial perspective. And that skill you all think of as like the basics. Like, of course, everyone can think about these problems from an adversarial perspective. But no, this is actually, it turns out, it requires a different kind of mind, a different kind of mindset to imagine this. After I've done creating my scheme, I now stop and I ask, what is every possible way that everything that I've been working on for the last 6 months could be wrong? I have to try and break the thing that I've just been building. And that's a really hard thing to do. And you know how to do that. You know how to think about this and try to say, well, OK, here are all of the assumptions that the person made. Under this one really weird configuration, here's how to break the thing. And just that skill is really, really useful. And so even if you use none of your experience with any of your FHE fancy stuff, just the single bit of knowing how to think adversarially could be really, really useful in this field, because the other people who are solving this, the language modeling people, don't have this skill, but are more than happy to try and solve their half of it. And I think the thing that is annoying as security people is we want to only do things what we fully understand, but that just means that very few of us are working in this space because we want to be fully right. But what this means is it's 99% dominated by the language modeling people who are not going to do any formalism. And I would sort of just you can do things that are not quite perfect and still have contributed a lot of stuff. So I got started in doing machine learning. Before that, I did return-oriented programming on I sort of was at Intel for a little while. I did pen testing. I have used absolutely zero of that skills in the last decade. None of the things that I know about how to finagle with the instruction pointer to point to a particular thing. I used to be able to decode x86 in my mind looking at the hex dumps. None of that was useful for what I'm doing now. But the single bit of knowing how to think about problems and try and attack things has been really, really valuable. And I think the same thing could be true for you. So I would just encourage you that you have the skills that are necessary, at least half of them, with this piece of it alone. OK. So I'll briefly conclude in the next couple minutes, and then I'll have roughly 10 minutes for questions, which would be great. So basically, all I wanted to say is that I think in the past, cryptography has tried to fix these flaws and make models more useful. And to be clear, we're not done. Right? I'm not saying we shouldn't be working on trying to solve adversarial robustness or adding privacy or doing private inference or any of these things. Of course, yes, we should continue doing those things. But now that we have new ways that models could be used to cause harm in the not too distant future, I would like us to spend a little bit of our time, not everyone here, but some of you, spending some of your time thinking about this problem. And I don't know, maybe next year at Crypto, there's I'm not going to hope for 17 papers, but I don't know, a couple of papers that roughly are saying, what if the models were harmful in some way? Here's how cryptography can try and help. With that, thank you very much, and happy to take any questions. Adi has a question.
First, thank you so much.
Yes.
The talk was really, really amazing. Thank you.
Thanks for a wonderful talk, very thought-provoking. I want to point out that there is a fundamental difference between the way the cryptography community is operating and machine learning. You described all in the early part of your talks how cryptographers tried to inject their techniques into machine learning, and you always ended up by saying it doesn't quite solve the problem. And we are not used to it. We are used to saying, if you use this protocol, then you have a proof of security. So somewhere there is a gap between them. And let me give you a concrete example of such a gap in the second part of your talk, when you talked about mitigating potential harms. I have an easy proof that you cannot make large language models non-fine-tunable. Because what I'm going to do is the following. I'll use the open source program, which is actually answering all questions in a great way, except for a small number of questions for which it will say, I refuse to answer. And then you add to it a small piece, which having seen that the main program refuses to answer, it will know how to generate Molotov cocktails and how to create Ebola viruses, etc. And it will replace the output. And I can easily combine the two by repurposing some of the neurons. So I believe it's impossible to make untunable. But it just demonstrates the gap between the two. We can give all kinds of provable guarantees in cryptography. You try to implement them in AI, and everything is mushy and cannot really solve the problem.
Yeah, no, I agree. Yes. So you have one counterexample. You could imagine though, what I could try and say is, what I want unfine tunable, or at least it's as hard to fine tune the model as it would have been to train a new model to answer those harmful questions from scratch. So in your example, you trained a new model that could do the dangerous things, and you patched it into the original. You could say, yeah, I agree it's very easy, but you could imagine that what the unfine tunable definition might need to be, that you might change the definition to say, I have not, by providing the model, sped up the process of allowing this. That if it took you $1 million before to make a model that could answer this question, it has not now become $10. And so you could imagine trying to tweak the definitions as you prove various pieces of it impossible. You could imagine trying to adjust the definitions until you get to the point where you can say the definition can't be made any better, or you just maybe it's true, this is outright impossible. And then that would just be really good to know, so that the people who are proposing these various schemes could just know this is a thing that we can't do. And I don't know, I want even impossibility results I would be very, very happy with.
Make a deep neural network which can answer harmful questions is a $10 task. I'm using the $1 million machine just in order to be an oracle which questions are harmful and which are not. So, and then I'm redirecting to the other program.
Sure.
So I'm misusing your $1 million, but not by directly answering the questions through the $1 million.
Yeah, okay, yes. We can talk about this, but no, if there's impossibility results, that would just be, I'd also be very happy with it. Other questions?
Thanks for the great talk. My question will be a little bit specific. First, for the AI safety, how I would like to see your insight about how the control flow attestation or remote attestation in the trusted execution environment can help the AI safety. This is the first question. Basically, that's asking how the attestation can help. And second is for model extraction. Can you tell us the hardness or the difficulties you might when you extracting the large language model, such as the randomness, and how deep you work on, how many layers, or is it real large language model? Thank you.
Okay, great. So the first question on attestation, which again, probably has all kinds of applications. One of the ones that people have been thinking about for attestation is exactly this. Maybe it's possible, that I could have a model that I wanted to prove had some property, and I can't prove it, entirely with, I don't know, fancy math. So instead, I just give you the program, and I say I guarantee you I'm running this program, and you can read the code and be like, yeah, seems good. If I can attest that I'm actually running that code, and maybe you're happy that way. I think there's lots of areas where you could rely on a mix between system security stuff and cryptography to maybe get some useful things. I don't know what you can attest though. Not my line of work. I don't can you attest this property? I don't know. Someone here almost certainly knows the answer to that, and they should just try and make it.
So the fine-grained attestation, you test it five instructions per se.
I don't know enough to be able to have an informed take here. Yeah, okay. Maybe yes, but I don't know. Someone should try. The second question you asked was on model stealing. And okay. So the model stealing attacks, the ones that we were working on with Eddie, are Okay. You need very, very high precision, 64-bit or more precision. It works like, up to 8 or 16 layers or something with, as long as you only have ReLU activations, as long as your model is like, 100,000 neurons or something, but like modern neural networks are like 1 trillion neurons, and they have all kinds of wonky activation functions. The attacks don't work at all at this big giant scale. We have a little bit of work that we tried at ICML to try and do stealing a tiny part of a model. So you have some giant model, we could steal the last 1 layer. Not more than that, not less than that, like we can get 1 layer, and like that was fun, interesting. I don't know, it would be interesting to try and ask, could you steal the 2nd layer? Could you steal the 1st layer? Could you steal the 2nd to last layer? I don't know, like this is a good question to try and think about. I think, again, sort of feels like a cryptographic shaped problem that I would be more than happy to have people here try and answer.
Well, I was just thinking about your definition of harm, of harmful LLM stuff, and it seems like there's a fundamental problem here, because I think if you try to enumerate the different harmful things that somebody can do with a large language model, you'll always cover a really tiny subset. Either you'll cover a tiny subset of the possible uses,
Yep.
or it won't be useful. Like if I want to understand, one of the things I will use Claude actually for is understanding some area that I haven't studied a lot in depth. If I decide I want to understand how, let's say, the adaptive immune system responds to vaccination or to exposure from a virus, you can use this. It's a very nice tool, but this fundamentally is also shortening the time for me to become somebody who can make a virus, right? It seems like there's a very fundamental problem here, and it's related to the way that when you try to set up a set of rules and you have a rigid small set of rules for thou shalt nots, you always end up having people do end runs around them. So that was just my thoughts.
Yeah, no, I completely agree. I think, yeah, this is why many of the things that I was proposing are not how to eliminate very particular harm categories, but try and like support things like independent auditing or something like that, where like you just like rely on a person to have done something, or support the ability to just like, I don't know, tell us whether or not certain categories of approaches are outright impossible, as opposed to, yeah, I don't think we should go like, whack-a-mole, one particular harm at a time. But like, if you could tell me, for example, that unlearning was just like not something that you could do. Like maybe it turns out that in these non-convex models, there's like, you've trained a model with gradient descent on a bunch of data. Maybe it's just a true statement that some individual examples will always influence the parameters in a certain way that you can't remove it. If that was true, it would be good to know, because there are certain categories of defenses I might have wanted to apply that now I can just rule out. And like, would be good to know that. Yeah, I very much don't want to encourage people to try and enumerate the list of bad things and stop only those things. Yeah, it seems, I agree. Yes. Yeah.
Rather than the sort of, I think and I really do think there's a problem with making a powerful tool that means it makes me more powerful. Well, then that makes me more powerful, and then that means I can do bad things.
Yeah, no, I agree that there are bad ways of setting the definitions, and we should try and avoid that. There was a question over here. While the mic gets passed over there, yeah. Okay, yeah, go ahead.
So I'm wondering, usually these machine learning models don't come with a nice explanation how they work, why they work, etc. So I'm wondering if we're trying to design solutions for protecting against them, how we should think about them. Should we try to think about them as black boxes that have unpredictable behavior, or should we try to go and understand all the details and like try to derive the explanations that are missing? Or is there some intermediate representation that you think will be useful that we should like start from? Like,
yeah, okay, so I don't know. I think, okay, yes, trying to understand exactly how all of the things work in the model seems kind of hopeless in some sense. Like, there are people who have spent a very long time explaining small pieces of it. And like, they might get a lot better. I think that like they've been making a lot more progress than I would have thought possible. But I think I wouldn't want to wait for them to finish their work before starting the work on how to do the cryptographic approaches that help with that. I think the most likely ways that I think people here could help would be trying to find things that you can say that don't depend on knowing exactly how the model works internally. Again, maybe like sort of this unlearning example, it doesn't really matter how the model arrives at an answer if I can show that it can't be removed. Model stealing as another example. It doesn't, I don't care how the model works. I treat it as a bunch of numbers, and I just study the numbers to see if I can extract out the bits. A bunch of the things that we've done in the past have had this flavor of, I'm just going to treat this as any other object and try and study it. And you're completely right that it's very, very fuzzy. But like, I don't know, there are ways in which you don't need to know exactly how something works in order to help out with that thing. Another example, I/O. I/O is giving you something over any program. Like, it doesn't matter what the thing is doing, you can give something. And of course, it's insanely expensive and everything else. But like, there's like lots of these kinds of things where you might be able to provide some value, even if you don't understand exactly how the object behaves in all possible settings. And I think, yeah, if there are approaches that do depend on the exact details of how it works, I'm somewhat more pessimistic that that's going to be very, very valuable. And maybe the answer, like maybe people try very hard, and the answer is just like nothing can be done because we don't understand anything. I don't know. I would feel pretty good about that, right? Like I don't know. Like, we have no proof of security for AES. Why do I believe AES works? Because a bunch of people have tried really hard and they failed to do anything meaningful to break it. Like, I could be convinced that like these problems we're working on are just like unsolvable if people in this community tried really, really hard and just like said like, look, I can't do anything. That would be good. Like, that by itself, I think, would be good to know that we have these problems that like are fundamental, and the best possible thing you can do is throw stuff at the wall and see what sticks. Like, it'd be very unconvincing to me. Like, that, I would not like that world. I would rather a world where we had like nice primitives we could rely on. But if we couldn't build anything despite people trying really, really hard, it would be at least good to know that that was the case. Yeah, but like, I will only get there if people try and see what happens. Yeah, thank you.